Hello everybody, this is second video. We are going to talk about the static loading conditions. So today I'm going to talk about Vollmer stress. So we remember when we have the static loading failure criteria for ductile material, we're looking at two different criteria mainly. The maximum shear stress criteria, which we discussed in the last video, and the distortion energy criteria. And this is where the Vollmer stress is used to compare with the yield strength of the material. So firstly, you have to do a little bit of quick comparison. Where is this problem come from? So in the static loading, we learned that we can use the maximum shear stress theory previously. Look at using sigma 1 minus sigma 3. This is twice of the maximum shear stress compared to SY, the yield strength of a material. So we can consider this two value, difference between two values. This is twice of the tau max as the overall loading of no matter what kind of complex situation you are under, the components under the loading of these two principal stress. And this can be compared with the yield strength of the material to tell if it's safe or not. So Vollmer stress is the same concept. We're trying to look at the material from distortion point of view. So if you want to distort a material, the shape of a material changes. So it takes energy to change shape. And from that point of view, the overall stress, okay, from sigma x, sigma y, sigma z, and all the taus all together can be simplified or accumulated together as a Vollmer stress. It's a sigma prime. And this single value then can be used to compare with the yield strength of the material to see the systems, the component is safe or not. So you can see both methods are trying to reduce from a complicated loading situation into something really simple. Only one value, or for the maximum shear stress, this is twice of the maximum shear stress. So the calculation part, for general case, the Vollmer stress is coming from the principal stress, sigma 1, sigma 2, sigma 3. These are the principal stress. We mentioned before, in three-dimensional space, you always have three normal stress and 3 shear stress. But you can rotate the coordinates somehow to get rid of all the shear stress and only have the normal stress. We call those normal stress the principal stress. And the Vollmer stress, basically you can get the difference between the two principal stress, square, and the difference between the other two, square, difference between the third group, square, then divided by 2 and do a square root. Okay? When we do our problem, in most of our questions and in our practical usage, the Vollmer stress is in a plenary kind of situation, which means you have sigma 1, sigma 2, you don't have sigma 3, or you have sigma 1 and sigma 3, you don't have sigma 2. So in x, y, z frame, you only have 2 out of the 3 values. So in that case, we don't use sigma 1, 2, 3 anymore. We use sigma A and sigma B. So this is a plenary principal stress. Okay? We don't have sigma C because that's 0. That's out of the plane. So Vollmer stress can be calculated with this. So simply, if you from the top one to this one, is you replace sigma 1 with sigma A, sigma 2 with sigma B, and simplify, you got this. Make sigma 3 equal to 0, basically. Get rid of that. And do a calculation. So this is if we know the principal stress, we can calculate the Vollmer stress. If we don't know the principal stress, so if we just start from sigma x and sigma y, and tau xy in a plenary situation, you can get this formula directly. Alright, so this is without getting sigma A and B. We still have tau here. We can use that to do the calculation. So for myself, personally, I only trying to remember this one. This is kind of the equation suits all the conditions. And then these two is for plenary situation. This is plenary principal stress. This is a kind of a general plenary situation. If you start with sigma x, sigma y, and tau xy, you just plug in and you get your solution. However, this is just lost the kind of understanding of where this comes from. And in the exam, that's the formula sheets in the exam. You can see we're using these two kind of equation. These two equations are given. Okay, so it's the plenary case because in our kind of designing of the shaft and stuff, even you have very complicated loading, eventually you got something is like kind of plenary stress condition. Okay, so this is equation we have. So obviously this is kind of the derived one. If you know the sigma x, sigma y, and the tau, you can directly put the numbers in and you get the result. Before we do those examples, because they are very simple, I wanted to get a little bit of kind of theoretical understanding of why this is the case. So if we have our component on the three-dimensional shape space, have the principal stress sigma 1, 2, 3, they are different in values. We can make that value into the two components. One is the average, the other one is the difference between each one of the principal stress and the average. So these two add together, see this is adding together, you got the original situation. And you can look at this first case, this part, because you can see three principal stress are the same, is the sigma average. So it means this is kind of, you are changing the shape of this cube. The geometry doesn't change. The angular distortion doesn't exist. This is only you make this cube bigger or smaller, depends on how much the stress is. And look at the second part, this part, because it's taking the average away, so these three values are different. And this is purely trying to kind of change its geometry. Right? So it doesn't change its size because average of these three are zeros. So average of these three stress are zero. So some trying to pull it out, some trying to push in. Eventually the size of this piece doesn't change. However, because some direction are different to the others, so this will become kind of distorted. And that's why it's called distortion energy theory. And we consider this part is actually causing the material to fail. Okay? Because you distort the material, the internal structure of the material kind of will be broken and cause the cracks and the failure of the material. Okay, so that's the theory behind this. Come to the calculation. So the energy, total energy of component under stress is equal to the stress multiplied with the strain. So certain force multiplied with distance, that's the work or the energy. And in the very micro level, we'll look at a single point inside the material. We'll look at the stress and the strain, so that's the force and distance. Then we put the Young's modulus equation in there, so the stress and strain has a certain relationship. And so you got a purely equation with only stress, no strain. Okay? And based on what we got before, we can have the average value in there. So this is kind of the average value in there. This is the distortion value in there. So the energy can be put into two different components. One is called hydrostatic energy, which is we take the average value, multiply with the average distortion. Then this is kind of can be calculated as over here. So this can be calculated, the total can be calculated from there. With this two, then we can get our distortion energy is this is equal to that minus this. Okay? And we put this bunch and this bunch in there, we end up to be having this. Okay, so this is the kind of the distortion energy in the component. And how do we compare? So this is our distortion energy. Okay? What situation when we can say the material is going to fail? We can consider the simplest case when the component under very simple condition is kind of only axial loading, so only sigma 1, no other values. In that situation, we know the component is going to fail when sigma 1 is equal to yield stress, because that's how we do the yield test. Okay? So we plug these numbers in there. So sigma 1, we got xy, sigma 2, sigma 3 is all zeros, and we got this. So this is when the system going to fail, at the boundary. This is when it's fail. And this is when system under that stress. Okay, if these two equal, then that means that's our failure criteria. So basically, this equal to that, or this needs to be larger than the yield stress to fail. Okay? You can see this part is all the same, so it can be get rid of. So it ends up to have this group of numbers equal to sy, or square root of this whole thing is equal to sy. Okay? And that's how we define the Vollmer stress. So this whole thing, we call it Vollmer stress. Okay? A little bit confusing is sometimes we write this same equation in a different form. So you can see this one. This one is written in a different form compared to this. Or that's the same. This two is the same. Okay, compared to this one and this one. What happened is simply you got the square, do the calculation. You got sigma 1 square plus sigma 2 square minus 2 sigma 1 sigma 2 and so on. Then the divided 2 will get cancelled out, and that's what's left over. Okay, so it's basically just did a calculation in there, and this whole thing is called our Vollmer stress. Okay, so we identified one single value that can kind of accumulate all the effects of different stress, sigma 1, sigma 2, sigma 3, all together into only one sigma. And this sigma can be used to compare with yield stress to tell if it's going to fail or not. So it's quite a good strategy. Otherwise, you have all different values you can't really compare. So if we draw this into a two-dimensional figure, so you don't have the sigma 3. So this is kind of a ellipse kind of a shape, okay, or oval shape. And the maximum shear stress is this dot line, this hexagon dot line inside. You can see this Vollmer stress uses distortion energy theory. It's kind of covers more area, and maximum shear stress is a smaller area, so it means maximum shear stress theory is a little bit more conservative compared to distortion energy. So when you have the same loading condition, these two theory, you get two safety factor. The one you get from Vollmer's theory, or Vollmer's distortion energy theory, is always going to be slightly bigger or safer. It tells you it's safer than the maximum shear stress. And in two-dimensional case, we just remember this one. This is a two-dimensional case where you know the principal stress. So when we solve the problem, like I said, it's always kind of in two-dimensional case. So this is the most kind of easy to use equation, 5.15. Okay? The Vollmer stress is sigma x square minus sigma x sigma y plus sigma y square plus 3 tau xy square. Then you do a square root. And once you calculate the Vollmer stress, this factor of safety is equal to yield stress over the Vollmer stress. So if we look at the problems, the tutorial 1, we have 5 cases for static loading analysis. We look at that from the maximum shear stress case, so we have to address this kind of a little bit with care, because some of them you don't, you have like both positive, both negative. You get one positive, one negative for the principal stress, then you consider the third one is 0. You don't just directly taking the principal stress out from here. But for Vollmer's stress, for distortion energy theory, you don't have to go do this one, because in here you have the shear stress. You don't use this one, or rather you use this one. So this one you get sigma x, sigma y, tau xy, which is just given. So just put the numbers in there, whatever you got, that's correct. You don't have to consider all the different cases. So actually doing this Vollmer stress using distortion energy theory for safety factor is very easy. Okay? You don't have to go solve the principal stress. Okay? So that's the tutorial 1 result. No matter what case, you put numbers in and get the safety factor. So compared to maximum stress theory, both of this theory is trying to kind of reduce the complexity of the loading into something with a single value that we can compare with a standard. So the standard is our material limitation, and Vollmer stress, maximum shear stress is the kind of 2 indicator can be taken to compare with the material strength. So here is probably the most usable equation, and it's also available in the exam. So to summarize, for the Vollmer stress, it is very important and to kind of combine kind of different loading conditions. You have different stress and shear stress, normal stress to be combined into a single number, and to use this single number to compare with yield stress, we can get the failure condition of a ductile material. Okay? For the maximum shear stress, we use this, so twice of the tau max to compare the SY. So hopefully when you calculate this in the exam, you get more clear with what's given here. So I'll go back again. So this is the equation we provide in the exam. So this one is if you know the principal stress, you do this. This one is if you just start with loading condition, that's what you use. Okay, thank you for watching this video.